Imagine you're standing at home. You need to know the absolute shortest route to get to school, the hospital, or the market. You could try guessing, but as a network grows, checking every possible road becomes impossible. We need a strict, systematic method. This is a 4-node graph. We'll set node A as our starting point, with weighted edges leading to B, C, and D. To keep track of our progress, we set up 3 tables: distance, visited, and parent. We initialize the algorithm by setting our starting node's distance to 0. The distance from node A to node A is 0. Since we haven't explored the rest of the map yet, we set the distances for B, C, and D to infinity. We use infinity as a placeholder for unknown paths. By assuming the worst possible distance for these locations, the algorithm only accepts a new route if it is mathematically proven to be shorter than the current estimate. The core mechanic here is called relaxation. It's a simple check. If a newly discovered path to a neighbor is less than the currently known path, we update our table with that lower number. Dijkstra's algorithm relies on a greedy strategy. It never jumps randomly across the map. Instead, it always scans the distance table and selects the unvisited node with the smallest known distance. Right now, that's node A at 0. We scan node A's neighbors, B and C. The cost to reach B is 0 plus 4. Since 4 is less than infinity, we update the table. The cost to reach C is 0 plus 2. 2 is less than infinity, so we update that as well. With its neighbors checked, node A is marked as visited. Looking at our table again, we check our unvisited nodes. Node C has a distance of 2, which is smaller than node B's distance of 4. Following our greedy rule, we select node C next and relax its unvisited neighbor, node D. The cumulative distance from our starting point is the cost to reach C, which is 2, plus the edge weight to D, which is 1. 3 is less than infinity, so D is updated in the table. Node C is now fully visited. Because all our edge weights are positive numbers, once we select the node with the absolute minimum distance and evaluate its neighbors, its shortest path is permanently locked in. We will never find a cheaper route to it later, so we never have to check it again. Based on the data in our current table, which node do we select next, and what happens when we check its neighbors? Node D has a distance of 3, making it the smallest unvisited node. We select it and look at its neighbor, node B. The currently known distance to B is 4. Our new path passing through D costs 3 plus 3, which is 6. 6 is worse than 4. The relaxation condition fails, so we leave the table exactly as it is. Node B is the final unvisited node left. We select it, but it has no unvisited neighbors. The search ends. We now have our final shortest paths. A to B costs 4, A to C costs 2, and A to D costs 3. Searching the entire distance table every single loop to find the minimum value is a major efficiency problem. For a 4-node graph, it's fine, but for a network with millions of nodes, scanning that array repeatedly creates a massive computational bottleneck. To fix this, we replace the standard array with a priority queue, specifically a min heap. This data structure automatically sorts the nodes so that the one with the smallest distance always bubbles directly to the top, ready for instant retrieval. Algorithm mastery requires both the mathematical logic to evaluate paths correctly and the precise data structure to supply the lowest cost nodes fast enough to be useful. This chart shows the exact logic we executed, mapped into a formal flowchart and pseudocode. We initialize distances, choose the minimum unvisited node, mark it visited, and relax its neighbors. The code then cycles through this process until no unvisited vertices remain. To remember this precise order of operations during exams, use the acronym IMVRS. Initialize, select the minimum distance, visit the node, relax its neighbors, and output the shortest paths. This mathematical foundation powered the first generation of consumer GPS units, calculating physical travel routes long before smartphones existed.
Today, that same core logic scales to the devices in our pockets, determining the fastest routes for ride-sharing and daily commutes. Dijkstra's algorithm reduces billions of possible route combinations into a solvable step-by-step procedure. Provided the system contains no negative edge weights, it will find the shortest path every single time.